all the participants from various institutions, industries, research scholars, students, and the faculty of Anna University gathered here. On behalf of Institute for Energy Studies, Anna University, Chennai, I would take this opportunity to extend my hearty welcome to the speaker of this session, Mr. M.G. Morshad, sir. He is a retired Deputy General Manager of Thermal Power Station 2 in NLC. He has graduated from NIT Jamshedpur and he has wide experience in control room operation of power plants, motor maintenance, transformer maintenance, and so. And he also a certified energy manager and auditor. He has conducted many energy audits. Also, he has published many research papers in various international and national level journals and also authored many e-books and he has delivered many technical lectures in various forums and we are very happy to have you here, sir. Now I request you to deliver a talk on your experience of energy audit at NLC. Over to you, sir.
Okay, thank you. Thank you, Mr. Sam. And it's a good afternoon for all the participants who are having connected now. I am a retired already, the introduction has been given. At present, I am staying in Bangalore. And from there, I am addressing all to you. And regarding these things, I want to tell one thing that this is I am sharing my experience. Only it is not a just like a research work or something. It is just my experience, what I have earned from during my service, and I have conducted two mandatory energy audit under PAT cycle 1 and PAT cycle 2 in 7 into 210 megawatt thermal power plant of NLC India Limited. So anyway, I have been asked to deliver my lecture on my experience in energy audit in thermal power plant. So in this regard, I have prepared my presentation. It's a mix of technical as well as the commercial aspects of energy audit in thermal power plant. Okay, because the time already has been given for the 2 hours. The topics is very wide. So I will go somewhat fast. And if you have any doubt, at the end of this session, you can ask or you can mail to me or you can WhatsApp to me so that I can able to answer all these things. Okay. Are you audible? Everybody is audible to me and everybody is hearing me? Okay. Anyway, second thing is that this type of technical session I am not used to, because normally so far I have taken classes on directly. But since last 2-3, this is the 3rd class I am actually taking, 2 for NPTI and this is for here. Also another it may come in future also. But anyway, it is not so convenient for me in coordination of the energy manager. It is very, very important because all are not expert in thermal power plant in all subjects. So that's why you have to make one internal team consisting of various system and subsystem, people from that one, and you have to prepare. Then scope of work, you have to prepare very clearly. Then tender terms and conditions. Then vendor list from the CA website. The tender processing. After that, data collection at the site in presence of internal audit team. Then prepare the draft energy report before interline energy audit team for any corrections, omission, and addition. And after that, the final energy audit team, and finally the releasing of the payment. These are all the steps, commercial and technical steps for conducting energy audit in any organization. Now, the accuracy of energy audit, it depends on the certain things like objectives. Your objective should be clear. Then scope of work, source of data collections, interpretation of the data and units, formula and calculation used, and final report format. These are all the factors which will make your energy audit report very accurate. Otherwise, if it is somewhat deviation, this one, that way is there, they will not be able rightly projected. It will not be projected properly, the conditions of the unit. Is it clear? Hello?
Yes, sir. Yes, sir.
Okay, right. Somebody should say yes or yes. Otherwise, I will not be able to clear whether my these are going or not. Anyway, now I will discuss about the objectives. Objective means what we are going to do. See, in any organization or any industry, the energy consumption line, what is called the energy consumption line, will be like this: Y is equal to ms plus c. What the fixed energy and the specific fuel energy, specific energy consumption, it will be like this. It is the design, particularly PG test. When it is the unit is PG test at the time new, so one line will be established. So that is called the initial or optimum design consumption line. With the aging factor or some other reasons, so this line took the deviation from the original line. So how much deviation has taken place? That is the concern for the energy audit. So energy audit find out the present operating energy consumption line, and they will compare with the previous line and try to give some suggestions or recommendation to make the line as closer as it possible. This is the objective of any energy audit. Is it clear?
Yes, sir.
Okay, good. So this is the objective of the energy. So one, the design energy consumption line will be there, and the operating consumption line will be there. So it will be always higher. If it is very closer, there is no problem. Normally 5%, 10% deviation may be allowed. If more than 10% is there, as per the PAT, 10% deviation, you have to make the corrections accordingly. So this is the objective of any energy auditing concept. So now, one another thing I want to say you. So energy auditing is not a calculation of the design value. It is only the comparison of the design, present line and the previous line. It is not necessary that I have to go for design calculations and other. Already the established line will be there, and you have to measure this what the conditions of the. Pardon? Yes. So the deviations should be considered, measured by the energy audit, and the recommendation should be made by the energy auditing team to reduce the deviation within 5%. That is the person. That is the basic concept of the energy audit. That is the basic objective. So how we are going to achieve? So we have to identify the area of energy waste. Where the energy waste is higher, that area you have to identify. Then quantifying energy waste, you have to quantify whether it is heat energy or electrical energy or other form of radiation energy, you have to quantify. And then benchmark you have to set. So this is the minimum you have to declare. So loss will be there. You cannot say anything without any loss. Loss will be there. Then you have to minimize it. And finding out the suitable measure for reducing the energy waste. So this is the objective of any energy audit and energy conservation. Is it clear? Okay. Now,
Yes, sir.
okay. Now the scope of work. I told you that the scope of work writing is a very big task, and it will go pages together, which will not be able to explain. So I try to make all these things in a pictorial views so that everyone can very easily they can understand. So this is the basic flow diagram of any thermal power plant. So fuel input will be there, boiler efficiency, turbine heat rate, and gross generation. Okay. So gross generation. So the first term will be coming the gross heat rate. So gross heat rate will be coming fuel input into GCV, gross calorific work, divided by gross generation. Three methods we can calculate: turbine heat rate divided by boiler efficiency, and specific fuel consumption, the GBC. So that three parameters will give the gross heat rate. So gross heat rate will be the conditions. It will show the conditions of the boiler and turbine conditions. If the gross rate is high, it means it will be consuming more fuel, more fuel. Efficiency is very poor. If the gross rate is minimum, it is very less. Means the efficiency is very good. After that one, another thing is the auxiliary power consumption. It is also connected with the same system. So when the gross heat rate will be connected with the auxiliary power consumption, we call it a neat heat rate. So normally, so when you see the neat heat rate, it will consider three things: boiler, turbine, and the auxiliary power consumption. So neat heat rate is equal to gross heat rate divided 1 minus percentage efficiency. So this is the very, very important flow diagram of any thermal power plant. So actually this diagram initially I drawn in 2013 and I published one paper in energymanager.com, handling power plant in thermal power plant, handling PAT scheme. I think this B has copied this thing in their PAT book. It will be available in the PAT book also. So when they released the PAT book in 2014 or 15, this diagram was also there. Anyway, just for a side reference I am giving. So is it clear this? I think,
Yes, sir.
okay. So I think a majority of the pupils are connected with me, those who are having experience in energy audit, in thermal power plant. I think it will be easy for them and they can able to guide it very clearly. Okay, next. So boiler efficiency, turbine heat rate, gross heat rate, auxiliary power consumption, and neat heat rate. These are all the four parameters is very, very important for the energy audit in thermal power plant. Okay, now how this is the scope, what I am telling you, this is the basic idea. Now the scope how to write. See, boiler efficiency, you have to calculate it. What is the efficiency? Boiler efficiency depends on the air preheater performance and economizer. So you have to prepare the scope for the boiler efficiency, air preheater performance, and economical performance. So the boiler system should be over. Okay. So air preheater and economizer, boiler efficiency one set. Then turbine, turbine heat rate. So turbine heat rate will be calculated. Along with this calculations will be, because the turbine heat rate, it also depends on condenser performance, superheater reheater spray, MS pressure, main steam pressure and temperature, then HPLP heaters performance, turbine cylinder efficiency, and turbine efficiency. So these are all the parameters related to the turbine heat rate. So you have to prepare the scope accordingly. So these are all the things you have to prepare. It is brought in the scope of work. Now, unit auxiliary power consumption, that is also very, very important. It has to be calculated accordingly. So it will be influenced by the excitation energy consumption, specific energy consumption of the mill, IDFD fan, boiler feed pump, CEP, boiler and turbine LT load, and ESP load. So these are all the electrical parameters which will be influence the auxiliary power consumption. Then stage and auxiliary power consumption. That is also a part of the auxiliary power consumption. So in such case, specific energy consumption of the DM motor, air compressor, ash disposal system, AC ventilation, lignite and coal handling system, fuel handling system. These are all the parameters to be given. Third is coming the stray energy loss. But there are some energy losses will be that stress, like steam leak, filling of the thermal insulation, water leak, etc. It will be influenced. So these are all the ideas. These are all the blocks that can be kept in the mind before preparing the scope of work. Okay. Now source of data. From where we'll be getting the source of data? Because thermal power plant is a vast area, people do not know from where the data should be taken. So that is also very confusion. But because of my experience, I have two energy auditing. So I decided all these things in my own and guided my internal and the external audit team to take the sources from there. So there are 4 sources of the data will be there. One is the DCS system, which will be available in the control room. Digital control system, what is available in all present thermal power plant, it is available. Second is direct instrument. Using the instrument, you can get some data. Third is the daily generation report. Every day in thermal power plant, what are the generation, what are the parameters? Yes, sir? Pardon?
No, sir. Someone is
Okay.
muted.
Okay.
That's why.
Okay. Just okay. I'm going on. You just say wishes, then it will be easy for me.
Sure.
I will be able to see. Okay? So, daily
Yes.
generation report. Daily generation report, it will be available with every shift engineer or the whatever it is. So, daily generation report and PG test data. So, these are the 4 things will be available. First, you have to try the DCS. If DCS is not there, if you have a doubt in the DCS, you can use the direct instrument. And some data must be available from that, like fuel analysis data, oil analysis data should be available with the shift generation. What is the auxiliary power consumption? These are will be available in the shift generation. That can be taken from him. And the PG test data in all thermal plants, when it will be starting, one PG test report data will be. If these data are not available, you can use this PG test data. But PG test data should be the reference. So with reference to, you have to take all these data generation. So whenever the energy audit team, internal or external energy audit team, try to do the energy audit in a thermal power plant, they have to fix first 4 source data source. Then only it will be possible for them to get the exact data from the thermal power plant. Okay, now instruments required. What all the instruments should be required? So electrical power analyzer for total power, kilowatt and PM, tongue tester for the current, gas analyzer for the O2, air, CO2, ultrasonic water flow meter for water flow, pitot tube for gas velocity, the flow, static and dynamic pressure, thermal imaging camera, high surface temperature, infrared detector, low surface temperature, anemometer, airflow, dry bulb and the wet bulb for humidity, lux meter for the light, and stroboscope for the non-touchable speed detector. So these are all the equipments, these are all the things should be available along with the energy audit team so that they can check all these things. Wherever it is necessary, they can utilize these things. Okay, this should be available along with the energy audit team. Now, data collections. When you are going to try to get the data collection, there are certain things is very, very important, which we are sometimes in the first audit, I have not done it. But in second audit, I have made it compulsory. So my data's reference has become all the time very good. See, these are all the things should be pointed. Data sheet means one book will be there or one log sheet will be there. From where, suppose you are going to take the data of the boiler. So you have to, in the data, in the sheet itself, boiler efficiency, before collecting the data, these are all the things you have to name of the system or subsystem. Then date and time, unit load, ambient temperature, humidity, air pressure, source of data, the name and signature, member of the energy auditing firm, name and signature, member of the internal auditing firm. So it will establish that you have corrected the data in presence of the energy audit. Yes? Yes? Anything? Any question? Hello?
No, sir.
Okay.
Actually, we have
Okay.
one. Okay,
Okay,
sir.
anyway, yes. So just I think my presentation is written is very clearly, so they can able to understand. Okay, so in each data sheet, it should be mentioned the name, everything, date and time, then ambient temperature, humidity, because these are all the things very uh, always have a big impact on the energy audit, particularly ambient temperature, humidity is very important factor. So these are all the points to be mentioned in the data sheet before collecting the data. Suppose boiler system, then you make all these things, what is the load, humidity on that day, time, at what time you are doing. After that, you start collecting the data, inlet temperature, outlet temperature, like this. So each and each and every data set should have a entry like this. Then your data collections will be perfect. Now, interpretations of the data and units is very important. I told you that energy auditing is not a research on it. It's not the establish the calculations. It is only comparisons. Nothing else is there. So if you try to establish the design formula and try to establish the design calculation, you will not be getting perfect results. So it is only some comparison, data comparisons. So units and interpretation of the data should be very important in this aspect. So normally you just see we sometimes measure the performance with the basis of the efficiency. We sometimes measure the performance on the performance, specific energy consumptions, and effectiveness. See, these are all the four parameters we always try to establish during energy audit. Either efficiency, performance, effectiveness, or specific power consumption, energy consumption. So these four data will be enough for establishing your, for units will be enough for establishing your energy audit. Nothing, there is no big things are not required. Is there the design aspect, the LMTD and others is there. This is basically used for the design purpose. But design data is not very important here. Rather, it is very important what is your operating condition with respect to the last data or the PG test data. Okay, is it clear?
Yes, sir.
Okay, next. Now, there is some established facts are there. So it is actually published by the BE. So there is a deviation, there is a changes or impact of gross heat rate. Gross heat rate's impact. Suppose the 20 superheater spray 20 tons variation per hour. So in 0.3 gross heat rate will be, it will deviations will be there 0.3, 0.8. Reheater super spray, MS pressure, MS temperature, reheater, all of the established data. So before doing all these things, you have to verify energy audit reports itself verify these established things. Then it will be easy for tracing out where the deviation has taken place. So this is a very important one factor. So how the gross rate, I told you the gross heat rate is one of the very important parameter in energy audit. So the deviation of the gross heat rate is established, already has established by the BE, and it can be verified with this data set and your what you are going to get from the local, you have to verify so that it will be somewhat accurate. Now, there is some explanation you need to you will have to give when there is a neat heat rate is there. It does not mean that neat heat rate always depends on the fuel quality or some other. So I have tried to establish there are so many variations are there. Suppose the heat rate, neat heat rate, I am not the gross heat rate, neat heat rate, variations will be there or it will be showing high if there is a variation in the fuel quantity. Suppose your first lot, the GCV is very good. Second lot, GCV is not good. So automatically your heat rate will be changes. Error in fuel measurement quantity. Suppose how much ton, because it is not a 1 kg, 2 kg, it's a ton wise the calculations will be there. So if there is an error in the fuel quantity, then you can see the heat rate variation. Low boiler efficiency also cause for this one. Higher turbine heat rate also cause for the this one. partial loading. Partial loading of the unit also caused by net heat rate. Partial loading for what? Suppose there is a fuel shortage. Technical minima. Nowadays, in ABT tourism, that Central Electricity or CEA, they will tell, or RLDC will tell to restrict their load to 150 for 2 hours or 30 hours. Like that, they will tell. That is called the technical minima. Low load schedule, what is called. Then poor condenser performance. Any other technical reason, the partial loading will be there. So this partial loading also reflected in the net heat rate. Then is aging of the plant. This is also one of the reasons for the net heat rate. Frequent shutdown and start of the unit. So every very frequent tripping is their unit. In such case also net heat rate will increase. Higher percentage auxiliary power consumption. So if the percentage auxiliary consumption is higher, that also lead to the net gross heat rate. So it is for what reason? Lower PLF. Suppose PLF is low, plant load factor is low, then fuel quantity variation that lead to the IDF define. Suppose the fuel quality variation is there, IDF define will take more power. Ideal running of operation, operating non-energy efficient equipment. So these are all the cause. See, sometimes that during the energy audit, they don't find out any reasons what they should write for the reason for the higher heat rate. So these are all the causes that can be caused. These are all the reasons that cause the higher net heat rate. So the energy auditor, internal or external energy auditor, they can use this idea, they can take this idea and give their justification for the net heat rate. So this is also very important things. What I did during my energy audit in my plant. Okay. Is all right?
Yes, sir.
Okay, right. Is it clear?
Yes, sir.
People are getting me? I do not know because I'm just one side I am talking about.
We're getting it, sir.
Okay, okay, good, very nice. So I think it will be helpful. Okay. Now, formula and calculations used. Okay. So how the formula should be established, how the calculation should be carried out. So I have tried to make all these things in the pictorial views so that calculations can be done later stage. First, the picture should be come in our mind. Then only it will be easy. Otherwise, it is very difficult to understand the situation because you know the thermal power plant is a very big plant and all applications of engineering are there. It is only one place where all engineering applications are available. The heat transfer uh, from one place to other, then electrical energy to mechanical energy, all energy conversions methodology are available here. So that's why uh, once people are getting experience in thermal power plant, they could be able to, you can say, utilize the 100% engineering skill in their life. So everywhere there. Being an electrical man, though my background is electrical and I was to carry out all the electrical activities, but during this period, during this energy audit, I learned everything from our mechanical colleague as well as the textbooks and other, and try to understand and try to make these things in a very clear manner. Because being an electrical man, I was not knowing what is boiler. So that's why first I established the things in the pictorial views in my mind. Then I try to understand. It will be very easy. I have made it in such a way so that anybody, irrespective to the branches of engineering, they can able to understand the thing, whether it is mechanical, electrical, both sides. I have mechanical and electrical, instrumentation, chemical, whoever it is. So they can able to understand the thing very nicely. So just you go how I am going to establish the some boiler system. Okay. So boiler efficiency. We can decide it, or you can measure the efficiency of the boiler in two methods. One is the direct method, another indirect method. In direct method, only efficiency you'll be knowing, and the indirect method, you'll be knowing the losses, what are the losses and what reason for the losses. Here only efficiency can be. So it at any time, if you enter the power plant control room, you can get all the data from there. Steam output. What is the steam is going coming out from the boiler? Steam temperature, steam pressure, and from these three data, you can get the enthalpy from the chart, molar chart, or you can say nowadays software it will be available. This is coming out from the boiler. What is going inside boiler? The fuel. That will be equal 210 per hour and NCB. Then indirect method is two methods we are using. What the NCB basis, another the fuel analysis basis. Okay, so NCB basis, what are the fuel going on, and what is the input to the feed water. So feed water temperature and enthalpy of the feed water. So boiler efficiency in NVC measure main steam flow in the main steam enthalpy minus feed water divided by fuel flow in the GCB. So I can very easily calculate within 5 seconds, 5 minutes I can calculate the 77% the boiler efficiency. So this is a direct method. But we do not know where the remaining 23% is going. We do not know. 77% is the efficiency. But where is the other loss? This 13%, 23% losses are there. In which form it is going? That we do not know. So this, for knowing this portion, you have to go for the indirect. Okay, indirect is somewhat typical, and mechanical people, those who have thermodynamics and paper, they have studied. They'll be knowing the boiler efficiency, how it is being calculated in the indirect method. One another method is there, that is the fuel analysis method. That is, it is called the percentage of the ash, moisture, and hydrogen. One formula is available here. In this, using this formula, you can able to find it out. This basis on the fuel analysis basis. Percentage of if you go for the fuel analysis, they will give oxygen, then moisture, then ash content, everything they will give, and based on that only you can carry it out the efficiency. Is it clear?
Yes, sir.
Okay, now. So if you just try to keep this picture in your mind, you can able to find out what all the parameters are required and how it can be calculated. Very easily you can calculate it. Now, boiler efficiency indirect method. So indirect method is a very descriptive method. You have to get so many data from the local DCS and somewhere fuel analysis there, everything is available, and with that only you can able to calculate all these things. So what are the data you have to get? First you have to get the fuel analysis data, GCB, ash, moisture, carbon, oxygen, hydrogen, nitrogen, sulfur. These are all the fuel analysis data you have to get from the laboratory. So they will carry out this data and give to you first. It will also be available in the shift engineer data sheet. Every day's data sheet it will be available. Then you have to take the bottom ash sample and percentage of the ash, GCB of the bottom ash. Then you have to get the flue gas analysis, percentage of the oxygen, carbon dioxide and CO2 before and after. Then air to air for conversions it will be going. So surface area, surface temperature, boiler surface area, then environmental conditions, the physical condition, environmental, wind speed, humidity, ambient temperature. So you have to collect all the data first. Then only you can able to go for the indirect efficiency of the boiler. It's a very typical method, and it's a very complicated method. So during energy audit, we should insist them to carry out this indirect report. Direct in daily basis we can carry it out, but the boiler, for calculating the exact condition of the boiler, we have to carry out the indirect method by the energy auditing team. They should carry out, they should collect all these things. Okay, now after that, these are all the data it was collected during this energy audit in India. The fuel, flue gas temperature, everything is available. Flue gas data, physical enable, all the data should be collected first. So from there, second. Next is performance calculation. You have to do the how much the theoretical air required, excess air, mass of the air supplied, mass of the CO2 gas, mass of the SO2, mass of N2 in the air, mass of O2 gas, and mass of dry flue gas. So these are the formulas, established formulas are available. And with this established formula, you can find out all the data accordingly. So you see the excess air 47%, and then moisture in the air is 4%, like that, kg per kg, sorry, or kg per kg of lignite, or everything is kg per kg of lignite except the excess air. So you can calculate everything very clearly by calculating the formula of this fuel data. Now, after utilizing this fuel data, you can find out the various losses. Heat loss in dry flue gas, that's L1. Heat loss due to the formation of the water. Heat loss due to the moisture in fuel. Heat loss due to the moisture in air. Heat loss due to partial conversion of C to CO2. Heat loss due to the radiation and convection. Heat loss due to the unburned fly ash. Heat loss due to burning. So finally, boiler efficiency will be coming 74.26%. So everywhere you can find what are the losses available. After that only you can able to trace it out. So which losses is higher and which losses is lower, you can identify very clearly and take the right corrective actions to reduce that losses. But before that, by seeing all these loss, the energy auditing team can recommend accordingly so that the highest loss can be reduced. Now, also there is a very important thing. See, there are two types of losses will be there. One is called the uncontrollable losses, another is the controllable. Uncontrollable losses means which we don't have any control over it. Okay, like moisture in the fuel. You cannot have a why the fuel is delivered. So it will be coming directly. So this we cannot deliver. Moisture in the air, depending on the humidity, water formation, and radiation. So these are called the uncontrollable loss. And controllable loss only dry flue gas, unburned fly ash, bottom. It is the controllable because it depends on the excess air. If the excess air is more, the dry flue gas loss will be more. And if the excess air is less, this unburned fuel will be less, higher. Unburned fly ash and unburned bottom ash will be higher because it will not be burned due to this not excess air. So if you have a right control over the excess air, this controllable loss can be reduced to some extent. But these losses cannot be reduced. That's why there are two parts are there. One part is the controllable losses, other is the non-controllable losses. Is it clear?
Yes.
Very important thing for the calculation of efficiency of the boiler. All are things I am related to the large side thermal power plant, and the boiler efficiency is the pulverized mill boiler. It is not the CBSC boiler and other conventional boiler only, because the things will change depends type of the boiler according to type of the boiler, but the guideline will be more or less same. the ideas of energy auditing will be more or less same. The same data will be there. Rather, somewhat you can say the calculation wise it will be easy to some extent. Okay. So by this way, the energy auditing team can be segregate the data and they can recommend the what actions they can take by seeing all this data. Now, fuel consumption pattern. It is very, very important because we do not know what is the pattern of the fuel consumption. Normally, during PG test, it will be established. After that, nobody will establish this one. So this is one opportunity. During energy audit, it can be established. But one thing is, the unit has to be run in the various load. If it is permitted, if it is possible, you can check it. 110, if you full load, it will be how much consumption. Then you reduce the load 180, then 150, 125, half of the load. I am telling about it. So at the time also you can able to see what are the fuel consumption in each load and primary the GCB of the fuel also you can see. Using these three data in the by using the Excel sheet, you can very well establish the diagram, establish a graph. In this graph, here you will see the 35 ton of lignite, ton per hour lignite is a fixed. Whatever it is load, so it is a fixed load. After that, it depends on the megawatt into this factor. So this 34 ton per hour, after that only it will go high. So this is the fuel consumption load variation graph with the load variation. So that is also one of the very good things. Though it is, I have not seen any other energy audit report, but in our plant we have established and we try to find out what is the minimum power lignite consumptions for the minimum load. So that is one of the good parameters for studying the boiler conditions of any thermal power plant. Now, how a gross heat rate and the specific fuel consumption. So first, each mill will be delivering some lignite or the fuel to the mill. So mill airflow, fuel flow mill A, B, C, D, F. We are talking about the pulverized mill, which is not ball mill. It is not there. It is available in the coal plant. I am telling about the pulverized mill is available in the lignite fired boiler. So whatever the mill is, what is the flow ton per hour, you can establish unit 1 and unit 2 like that. And the total air flow, total fuel flow, you can establish, you can decide it in the, you see there's a design value 210, here I am getting 298. GCB of the fuel is the same. So total energy input, you multiply this one, and total heat generation of the dishes. So total gross heat rate you can calculate accordingly, and specific fuel consumption you can calculate accordingly. So gross heat rate 2650 is a design. Now in unit 1 is 2761 gross heat rate, specific fuel consumption 1.04, and here it is 2870 1.08. So you can establish the gross heat rate and the specific fuel consumptions in any power plant. Okay, it's clear?
Yes, sir.
Okay, good, very good. Now, economizer performance. So normally, this type of things, we are checking the effectiveness, how effectively heat is being carried out. So in economizer, what is happening? The hot flue gas is going out from the boiler and feed water is going to the boiler. So heat exchange is taking place and heating up the feed water is done by the heat loss. So the flue gas will lose heat. At the same time, the feed water will heat it up. This heat exchange between flue gas and the feed water depends on two things. One is the scale formation inside the water tube, or other outside the soot formations of the gas. So if the thickness of the soot is more, all the weight will not go here. Or if the soot is scale formation in the pipe is more, all the fluid. So one side is gas side effectiveness, another is the water side effectiveness. So actually effectiveness we are calculating depending on the heat head. Heat head is the maximum heat deviations. See, this is the inlet temperature 243 and fuel inlet water temperature and inlet flue gas temperature. So difference will be the heat loss. It is called the heat gain. This is called the heat. This is called the heat head. These two difference of the two is called the heat head. So from the flue gas side, with respect to how much it is going and how much in water side, how much it is. So that we are calculating here. The heat loss in the flue gas. So flue gas inlet and flue gas outlet. So 162. Heat gain in the feed water outlet, feed water inlet. So 93. So water side effectiveness. So heat gain divided by difference between the two temperatures. That is called the heat head, maximum heat head. So maximum heat head, this is. So 40%. Gas side effectiveness, gas heat loss, and the heat head. So 71%. So low effectiveness water side indicates the scale formation in the tube. And low effectiveness water side is called the soot formation in the tube. So by checking all these things, you can find it out whether the scale formation is there or whether there is a soot formation set there. If the soot formation is there, you have to go for the soot blower for cleaning the soot. And if the scale formation is there, you have to check the boiler water, whether boiler water chemistry is proper or not. Because if the chemistry is not proper, there is a possibility of scale formations in the tube. So that may cause the. So economizer performance is very good. So how much heat is going inside? If the performance is very pure, the boiler efficiency will also decrease because heat is not being heated up here. So automatically it will be there. So you can take the energy auditing team can take this remarks or take these observations and give their recommendations. Now air preheater system. So if you go to the air preheater system, there is a boiler. The hot flue gas is going here, going to the ESP, ID fan, and then it is coming out from the chimney. If the fan finished, air is sucking from the atmosphere, it is going to the air preheater, air is getting heated up and going to the boiler. So the air preheater is the main thing where the heat exchange takes place. The exit flue gas temperature will lose the heat and same heat is going to the air. After that it will go here. Likewise, so if there is some problem, if there is a proper heat exchange is not taking place, automatically what will happen? The boiler efficiency will also reduce. So 1%, 21% boiler efficiency if the 20-degree increase in. So if the 20-degree increase in the exit temperature we are measuring here. If there is a 20-degree, so 1% boiler efficiency will be lost. This is established fact. So you have to see the performance of the air preheater, how it is being performed inside. Is it clear?
Yes, sir.
Okay, now how we are going to check the low performance of the air preheater because of the various reasons. One is this dirty or aging baskets, where basket will be there. Then air leak and air flow bypassing ASP. So the three reasons that will not give the performance of the air preheater. Suppose there is a clog in the baskets, the air pass not took place and the heat exchange will not take place. If there is a air leak, that it is a big body, it's a big size air preheater. So if the sealing is not proper of the air sealing, so what will happen? The air will leak from this side to this side. So automatically it will not heating taking place. And sometimes what will happen? It will not going to here, it will bypassing the air preheater and go. So there are the three things which will be deciding the performance. First, the gas size effectiveness. Okay, I tell you the total heat head, flue gas temperature if, before and air temperature before AFP. Because flue gas will be going that side, this way. So flue gas in flue gas exist flue gas temperature is in air temperature. So difference between two is called the heat head. I just perform for checking the performance difference between two heat head. So gas temperature, flue gas will be losing temperature here and air will be getting. So when the flue gas temperature losing divided by the heat head, you get gas size effectiveness. Similarly, the air temperature increases, gain, air temperature gain defined by heat is the gas air side effectiveness. So these are the things we are calculating. There's the one thing. Second thing is the air leak, how it takes place. So air leak is measured by seeing the O2 or CO2 before and after the preheater. How much percentage O2 is there and how much percentage O2 is there. So based on that, this data will also be available in DCS, but for the cross checking, it is better to check at the local itself. We have to take the fuel analyzer and take the flue gas before and after, analyze it, and how much percentage O2 and how much percent CO2 is there. In both cases, it will be there O2 before and O2 after. Then one formula is there. Then you can say this is. Normally 10% is allowed. If it is 10%, then 8 to 10%. If it is more than that, it's a very severe condition because your efficiency of the boiler will not increase, whatever the try. So you have to arrest the air preheater first if it is 10%. So it also indicates when you measuring all these things, the energy audit team can recommend for replacement of the or replacement of the air preheater system itself, either basket or the leak. They can consider it. If the leak is more than 10%, they can very easily recommend for arresting air leak by changing the sealing. They can very easily. Changing is not a very big matter, but it can be done. So by this way, we can able to understand. Now, one another factor that is called the X ratio. What will happen in such case? The air will not enter here. It will bypass and go. So that is also the loss of efficiency of the boiler. So this is called the X ratio. So it is some standard value is there, but it is not a standard all the time. It should be minimum as possible. So you see the standard is 0.67, but here it is 0.7 higher. Means there is a air leak is there is a bypassing is there. So this is called the X ratio. The three parameters you have to check in the air preheater so that you can able to identify the conditions of the air preheater. Is it okay?
Yes, sir.
Okay. Now, performance. Then how you are extracting the meaning of such activities. So higher side effectiveness, gas side, exit flue gas temperature, higher differential pressure, higher X ratio, higher air take. So if you have an idea all these things, you can very easily give the recommendations and very easily you can arrest the leak or correct the things very easily without any big expenditure. Because it is that recommendation with the expenditure is also a very important factor. Suppose if you tell entire boiler should be replaced, then it is not possible. Nobody will be interested. But the energy auditor firm, If they recommend very small measures but huge loss, it will be accepted. So these are all the ideas. If they have in their mind, they can able to give a very less expenditure for correcting this matter. That's the main purpose. It is very easy to give all the recommendations, but at the same time, they have to see how much investment the power plant have to do. If the investment is very high, nobody will be interested. So if the investment is very low, with the operation and maintenance cost it can be carried out, then everybody will implement it. But unfortunately, majority of the energy auditors nowadays available, I do not know what I'm telling about 2 years back condition. They were not able to understand that thing. They will give so many huge recommendations, which is not possible to implement also sometimes. Okay, so these are all the things. But because why they cannot be able to do all these things? Because they are not studying and they are not seeing what exact the way of doing the things. That is the basic things what I understand. Now draft system is there. So what is there? FD fan, it will suck the air from atmosphere. Then it is going to the air heater. It will heat it up. Then heated up air will go to the wind box. From wind box, it will be distributed and it becomes a flue gas and going back to the ESP and chimney. So this is the air circuit. Okay. In this air circuit, there is this side, FD fan will be loaded. If there is a leak, so air will come out. If there is a leak in the wind box, if there is a leak in PF duct, if there is a leak in the air heater, so what will happen? Unnecessary water, unnecessary air has to be sucked by the FD fan. Only part of it, only 70% will be, 30% will be waste. So in such cases, FD fan will consume more power. Likewise, the boiler should be always operated in the vacuum because it will be sucked by the ID fan. ID fan size will be very bigger than the FD fan, more or less double. It's a 900 kilowatt, it will 1800 kilowatt like this. So it will suck the air. So from there, boiler side, it will be the negative pressure. So when the negative pressure will be, if there is a leak, so air ingression will take place. So ingression will take place in the ID fan, flue gas part, and ID fan will be unnecessarily loaded. So that will consume more power. So that's why in this path it said that to keep the ID and FD fan unnecessary loading, the arresting of the air should be there. So before that, you have to calculate, you have to identify whether it is how much excess power it is taking, how much excess power ID and FD fan taking, and what is the fan performance. So this is the very important thing for the duct system. Okay. So for that reason, you just see the FD fan, two FD fan will be there, air heater will be there, then conversion will calculate it, then air heater. From there, it will be the actual air for the conversion. So FD fan data you have to collect everywhere. What is the air density, that discharge flow, air temperature, density, discharge, measuring discharge pressure, suction pressure. These are the data you have to collect from the local itself or the if it is available DCS, you can collect it out. Then you have to calculate the fan efficiency. What is the fan efficiency? What is the design and what is your actually operating? So you see the design 74, but you are operating at 67. After that, you have to go for the motor loading. What is the percentage? See, percentage motor loading is 42. Normally, the designer has given, but you are loading at the 40. Specific fuel consumption, it is 1.02 designer has given, but you have operating 1.12. So at least 0.02, 0.3, 0.1, this is possible to reduce. So excess power consumption is 47 kilowatt. So in ID fan, if you see that with respect to this one, design value, 47 kilowatt you are consuming. So once 47 kilowatt is consumed by your ID excess, then automatically your auxiliary power consumption will increase or your neat heat rate also will increase. So by this collecting the data, so FD fan, motor loading, efficiency and specific power consumption. The three important things you have to measure. Likewise, ID fan from boiler, the two parts will be there. So it is coming from air preheater. Here, if the leak is there, the air, because it is a vacuum, so air will go inside, sucked. Then ESP. From ESP, you will be remove the S. After that is going to IDA and IDP. Then it is going to the chimney. So if the air is not removed properly, S is not removed properly, what will happen? If the performance of the ESP is very poor, automatically ID fan will be loading. ID fan will give higher loading. It may trip sometimes. And at the same time also, what is going to happen? Your auxiliary power consumption also. Suppose your fuel is very, ash content is very high, sand content is very high. What will happen? The ESP, it will not be able to extract all the required weight of ash or sand from the flue gas. So automatically what will happen? ID fan, FD fan will also be loaded. So performance of the ESP, then quality of the fuel is also very important for auxiliary power consumption. Is it clear?
Yes, sir.
Okay. So that's why the GCB of the fuel should not be as you like. So there should be some segregation should be there. There is a stand. Otherwise, what will happen? The auxiliary power consumption will also be increased. Okay. Now likewise, what we have done, motor loading, efficiency, especially power consumption, all the data we have collected. After that, fan efficiency, you see the 81% efficiency, but where we are seeing the 76%. Okay, motor loading, 85%, but here it is 95%. You see the designer has given 85, but here they have given 95. See how much overloaded the motor is. So specific power consumption 1.09, 1.9, here 2.07. So excess power consumption is 145 kilowatt. So 145 kilowatt, where the excess power, you can say the auxiliary power consumption. So automatically your auxiliary power consumption will increase and your neat heat rate will also increase. So when you will be going for auditing, only simple recommendation will not be enough. You have to see what are the causes and what are the reasons for this overheating or neat heat rate or the gross heat rate. So these are all the indirect topics because sometimes the energy auditor will not be able to identify or further they will give a very plain things. What the main things they will give, then the fuel quality is not good. Simple reason they will give. But changing the fuel quality is not very easy for the thermal power plant. It's not very easy because they have to get from the same mine, they have to get from the same rate. There is a variations is the rate also be there. So they will recommend and go. And automatically what is going to happen? They will not able to implement all these things. Rather, if you give this type of example or this type of study, you can simply tell, sir, these are all the things are there. So not only fuel, there may be some leak is there, air ingression is taking place. That's why your ID fan is loading more. So you try to arrest it. Arresting the FD fan, ID fan air ingression, ID fan route air ingression is easier than changing the fuel quality. So these are all the way the recommendation should be given. Otherwise, The recommendation which is very costly or which is not practical at all should never be implemented. It is not possible to implement also. So before, that's why in my team, I requested all the mechanical and all my internal energy team to try to accept such recommendation which will be easy to implement within 5 years with low investment. So we recommended several times. No, you change the views. You give recommendation like this. Then it will be able to understand. It will be able to implement. Otherwise, it will not be possible to implement. So I request to energy audit team, those who are participating here, external or internal, they must look into this matter, and based on these recommendations only, based on their observation, you try to recommend the things which will be very easy to accept and investment is less, and the return will be within 5 years. Then the recommendation will be possible to implement. Otherwise, it will not be possible to implement, because nowadays there is all the thermal power plants are running in a very you can say critical stage. What I'm telling, after that tariff regulations and other comes, so it will not be very easy to implement. Now, uh, I think I left only half an hour, isn't it, Sham?
Yes, sir.
Okay, okay, okay,
40 minutes we have, sir. Yes.
okay, right. No problem, no problem. I'll go
Okay.
on. I'll go on. No problem. I'm having content. I'll go. No
Sure,
problem.
sure, sir.
Okay, right. Now, I'll be going for the turbine system. Again, I have tried to visualize everything through the diagram. So, turbine heat rate, how you are going to measure. So, turbine heat rate. So, if all the operating data, if you go to the unit control room, you will get all the data from there and you can make the turbine. So, first you have to note down the MS pressure, MS temperature, pressure, and enthalpy. Main steam 660 ton per hour, temperature 530 degrees centigrade, pressure 150 kc. So, temperature and pressure, if you see, automatically you will get the enthalpy. Okay, so main steam. After that, cold reheat it is coming. So same thing, cold reheat also, you check the ton per hour, then temperature, pressure, and enthalpy. Then after reheated from the boiler, again it is the IP turbine. IP turbine. After this is called the hot reheat, cold heat or hot reheat. Hot reheat also you can say. Then it is going to this IP turbine, exhaust hood, then condenser. And from the condenser, again it is coming to feed water and going back. So this is the total flow diagram of measuring the turbine heat. So these are all the things you have to see. What is the MS condition? What is the cold reheat, hot reheat, feed water? So by using this formula, MS flow, MS enthalpy and feed water enthalpy. Okay, into then hot reheat flow, hot reheat enthalpy and cold reheat enthalpy divided by unit. So this will be calculated the heat turbine heat rate. 2112 kilowatt, 2112 kilocalorie per kilowatt hour. So this is the method of calculating turbine heat rate by taking the data from the unit control room. What is the load available? According load, you can do it. Okay, very easy to understand and very easy to remember. If you go for the diagram and calculation, it will be boring, as well as you will not be able to understand what we are going to do. We are going to see the how much heat is input for generating 1 kilocalorie of water. So heat input is given to the turbine, because the energy conversion taken place in these three stages. The heat energy is being converted to the mechanical energy. Okay, so see, the energy conversion is taking place in three units of high pressure turbine, intermediate pressure turbine and low pressure turbine. And with respect to how much heat is required to generate a mechanical power of 1 kilocalorie per hour. This is called the turbine heat rate. Okay. Now, turbine HBD curve, heat balance diagram curve, actually this will be given by the manufacturer along with this turbine, because the turbine heat rate will not all the time same. It will be over a particular time, because the load is very less, the heat rate will be high, because it will take more energy to produce the secret. I am telling that there is some specific power consumption is there, all the equipment. So you cannot say that it is depending on the load. It is depending on the specific power consumption. So 60 megawatt, this much it rate, 75. These are the data should be provided by the manufacturer. On the basis of that, we have to plot a curve, and this is the formula we have to establish. I think those people who are in the energy manager in any plant during part cycle 1 and part cycle 2, this graph I think has been given to the BE as a reference, because with the base of that only they can consider because our units are not running all the time in the full load. So they will consider the heat rate according. Suppose your average load is 180, they will consider this. Your average load is 150, they will consider this. Likewise, the heat rate, they will variation based on this graph. Because during my period as the energy manager, already I have submitted this graph to the BE, so that they can consider the this one heat rate. This one turbine heat rate card. Turbine heat rate, they will change according to loading practice. Okay. Now, similarly, fuel consumption, then we can establish the steam consumptions also in load variation. It is normally carried out during a PG test, but you can re-establish it, because PG test has become, suppose, 30 years old power plant. PG test was carried out 30 years back in 1980s, 85. Now it is 2021. So there will be deviation, huge deviations will be there. So every 5 years or 6 years, that should be carried out to establish that internally the unit should carry it out once in a 5 year, so that they can able to establish whether their aging process is high or not, because it normally happens with the aging process. So consumption will increase. So to establish it, we have to take in various load, like boiler fuel consumption, we have to establish the ton per hour fuel consumption, we have to record it, the steam generation. So for that, how much heat is there, heat energy, steam enthalpy, required steam flow, and actual steam flow. So based on that only, we can deviation find out, and we can actual field establish, and you can establish the graph utilizing your Excel sheet. So when you are established this thing, you can able to understand how it is, what is the minimum steam consumption and how it is changing. That is called the wind curve, I think. I think it is some another name was there, wind curve. But I try to establish these things in our plant in all units, so that we can able to understand the aging process of the plant on the steam consumption, steam loss in the plant, and we can also establish that this much energy is being lost due to the steam consumption. So that can also be recorded. Now another thing is the turbine cycle efficiency. I see turbine efficiency and turbine cycle efficiency is entirely different. This is turbine, generator, and condenser. So majority of the heat energy is lost in the condenser through cooling tower. Normally, the turbine efficiency will be around 40%, turbine cycle efficiency. 60% will be going to the atmosphere through the cooling tower. Majority of the heat will be there. So how you are going to establish? So turbine heat rate, we have to design an actual calculate. The generator load, actual and this. Then turbine input. Turbine input means divided by efficiency. Generator efficiency, turbine input, it will be there. Okay. Then turbine output. So turbine input will also heat rate. How much heat rate will be there? Multiply in the with this one generator load and this. So you will get it. So turbine cycle loss T1 by T2. This is. So turbine cycle efficiency is a purely mathematical and thinking you can do all these things. It is nowhere you will get in the book. It will be established by me during my energy audit. It is not available there. So you can see that actual this one efficiency is 41% and design is 42%. Though it is somewhat conservative values, normally it should be 38 to 39. Okay, so actual. But design value also, it will be around 41. So some discrepancies are there. So these differences, you can say the 15 megawatts, around 15 megawatts we are losing in the system. So this is called the turbine cycle efficiency. This is for the academic purpose, you can establish and think it. Now turbine cylinder efficiency, it is by the molar chart. You have to go to the molar chart and you can see the mechanical people, those who are purely mechanical and turbine specialists, they can understand these things very well. So heat 1, heat 2, heat 3, these are all the inlet steam pressure and enthalpy of the outlet spin probability. So these are all the things available. You can go to the molar chart, you can able to establish and you can understand better. Being an electrical man, I may not be able to explain very clearly, but my mechanical friends, they can understand and they can do the things very well. So as per their advice, I have taken that one as a reference and you can also carry it out the same thing. So these are all the calculations. So targets. So finally, the HP cylinder efficiency 76%, IP cylinder 90%, and LP transport 90%. So the cylinder efficiency will be very high. But the cycle efficiency, total cycle efficiency, include the condenser, it will be going very less. Okay, so this also has to be. So these are all now very important. But as a background, you can put all these things. And nowadays, the software is also available. You can put the data automatically. They will give all the data accordingly. You need not have to calculate. All the data should be input there. I did all these things manually because at that time I was not doing. But nowadays, it is available in the software also. So you can establish this one, the cycle efficiency also. Now, LP and HP heaters, because the water coming to the boiler feed pump or to the boiler, coming through the HP and LP heaters, through the HP and LP heaters. It is called the preheating stage. So, condenser, it will be coming back to the normal temperature, then preheating will be taking place, and after that only it will be coming back to the boiler feed pump and the feed water. So when the preheating is taking place, normally steams are extracted from the turbine and it is put in the cage. So water flow will be like this. Steam will be going here and coming out. So steam energy will be condensed here and drain will be come out. And the heat exchange will take place. So normally this thing will be measured in this performance of this one TTD, terminal temperature difference, or the drain cooler, this one, the drain cooler's temperature. So these things will be. So the difference between extract steam temperature and pressure and the outlet temperature is called the TTD. And the drain cooler condensate is this from outlet to the inlet water. So both way we can measure it. TTD is the better way of performance, calculating performance. So TTD normally we are measuring basically for the TTD. TTD normally 3 degree will be the difference will be if the TT degree is higher, the performance is very poor. If the theta degree is lower side, the performance of the heater is good. So normally we'll take 3 to 5 temperature degree will be the standard. Drain cooler condensate approach, drain cooler approach, what I am telling you. So drain cooler approach is level of the condensate. So this also one. So typical temperature will be 10 degree. Okay. So we have established a plot like this, and everywhere saturation temperature LP heater 4 up to 6. We put all these things. So these are the designated TTD. Condensate temperature rise, effectiveness we are calculating. So up to effectiveness, you see the actual TTD is 17. Here this design is 3. So the performance is not good. Here performance is more or less okay. Here it is not good. Here more or less okay. Here is very good. So by seeing this data, you can able to justify or understand which heater is working properly and which heater is performance is good or bad. After that, you can, for academic purpose, you can come this direction. So these are the design aspects actually, LMTD and other. The TTD, the design TTD and your TTD, the difference will be very, very important. Because how much heat exchange is taking place, that it can give the exchange. Other than the effectiveness also, you can carry it out, all these things, especially then heat calculations also carry out. So by this way, you can able to understand the performance, calculate the, identify the performance of the heater. Now the condenser. It's one of the very good aspects. The temperature profile of condenser, I do not know, but after a lot of studies, I have made this graph. I get some reference somewhere. Based on that, I redrawn it and I made this one. It is available with me only. I do not know who is following or not. Basically, for condenser performance, we are worried about the condensers only for the vacuum loss. We do not know for what reason the vacuum is lost. So if the vacuum losses take place, automatically the performance of the units also gone down. So we have to identify where the vacuum loss is, what is the reason behind the vacuum loss. Okay, for which this temperature profile should be there. One is the temperature is hot oil condenser temperature. It will be available in the unit room. Exhaust fluid temperature, it will be available in the approach. Then circulate over inlet temperature, circulate over outlet temperature. So this is called the difference between the hot oil and exhaust tube. It will call the subcooling temperature, TS. Subcooling temperature. Then difference between the saturated and TA2 outlet temperature. It is called the approach, TTD approach. And temperature is T1, circulatory temperature T1 by T2. And that range Ts by T2 is calculated. So these parameters are available in the control room. And you can take all the parameters and plot a graph like this. Plot like this. So circulating water temperature rise, then TTD and subcooling. 3 factors you just plot. And these are the reasons for the low vacuum. So first thing is the reason for the low vacuum, low condenser vacuum, low cooling water flow, high inlet cooling water temperature, suppose due to the climatic condition. If you measure all these things, there will be heavy diffusion will be there in this. Others will remain same. At the time you can say it is due to these 2 conditions. Likewise, when there is a tube falling will be there, this temperature, TTD deviation of the TTD will be very high. Other two should be very minimum deviation. So you can say that tube falling. Suppose there is a condensable gases are there. In such cases, the subcooling temperature, these deviations will be higher. Other two will be very minor. And if overduty is there, overduty means excess. So higher deviation both, there will be minor deviation. So by seeing these differences, you can identify what is the reason for the condenser, what is the reason for the vacuum, a low vacuum condition, because low vacuum condition is a majority of the reason for the partial loading. When the vacuum is low, we have to reduce for the condenser. A condenser cleaning, everything is not very easy. First, you have to establish for what reason. After that only, you can. It can be done during performance checking of the condenser also. Those who are doing in the performance checking on monthly basis or half yearly basis, they can very well take this data and monitor it very easily. It will be very easy to understand and very easy to carry out the exercise. Now this is the condenser I have given. The saturated temperature, this is a condenser or inlet water, outlet water. So TTD, what I am telling you, LMTD, everything, you can calculate it. And you can see these are all the parameters calculation I have done actually in this thing. And finally, condenser cleanliness will be the factor. Design 85%, our is 66, 67%. Means condenser is not clean. It may be external, tube falling or something. Is it okay?
Yes, sir.
Okay, right. No, because I do not know. I am talking just like other side people are sleeping or not. I do not know.
Yes.
Okay, anyway, because
Okay.
this is the one of the tragedy of online classes. See, you do not know who is listening to you. There is no eye contact. Whether my lecture is properly reached to the person or not, that also I'll not be able to understand. Just I'm talking to the wall also before me. One wall is there. So sometimes you say at least yes sir, then it will be easy for understanding. Okay,
Sure, sir.
okay. So like so cleanliness factor is there. So vacuum is optimum when the condenser vacuum is higher than the design vacuum, hmm, corresponding to the same exhaust fluid temperature. Okay. Vacuum loss occurs. The vacuum is optimum when condenser vacuum is higher than the design vacuum, correspond to the same exhaust fluid temperature. Vacuum loss occurs when condenser vacuum is lower than the design vacuum, corresponding to the exhaust fluid temperature. So 1 mm loss of vacuum is somewhat 5% loss of something, they have given it. Okay, so these are the established fact and established design. Okay, now I am coming to the cooling tower, the natural cooling tower. So hot water going there and cool is coming out. So the difference between A and B is called the range. How much range you can reduce? Range means this variation to this variation it can able to reduce. That is the approach is ambient temperature and the outlet. B minus C is called the approach. Okay. So approach is the with respect to the ambient temperature and outlet temperature. So B minus C. If ambient temperature, so approach is higher, approach will be higher when the cooling effect is more. Okay. So these are the range and approach. These are the two things by which we can able to calculate the effectiveness of any cooling tower. Is a normal. Pardon? Hello?
No, no, sir. They have unmuted suddenly.
Okay, right.
Okay.
Okay. Okay. Now, there are long calculations are there. This approach is a very operational people's, they will carry out once in a while, once in a 10 days, once in a 15 days, or daily basis. But this is the normal approach for normal things of performance monitoring of the cooling tower. But when you go for the performance means energy audit, in such cases you have to go for the some uh, authentic this one, you can say, uh, calculations. So there also evaporation loss should be calculated, then effectiveness should be calculated, then air water flow, all other parameters to be calculated during operation. Inlet water, some what all the things are available, with on the basis of this data, you have to carry out all the details diagram. Then it is only applicable only for the energy audit, so that you can able to see what you see. So effectiveness is 64, but where the effectiveness calculated is less. So that means the performance is not in a good aspect. So these are all the broad line. Suppose air-water ratio increases with the decrease of the airflow. Low range indicates insufficient water flow. Low approach indicates higher city size. Approach city size, cooling tower size. Low effectiveness indicates poor performance. Higher evaporation loss indicates good performance. So evaporation is more, means the performance is very good. Low effectiveness, the poor performance. So these are all the key observations related to the cooling tower. Okay. Now I am coming to the electrical system directly. If you see the auxiliary power consumption in an electrical system, the generator will be the generator transformer. The power consumed by the self-consumption is called the auxiliary power consumption. It can be taken from two sources, one from the own generation, another from the grid itself. So from the grid, it is called the station consumption, and own, it is called the unit consumption. So total consumption, the auxiliary power consumption should be station consumption plus unit consumption divided by station generation. This is called the auxiliary power consumption. So auxiliary power consumption will vary depending on the type of units. Particularly lignite fire boiler, the auxiliary consumption is very high because we have to uh, run the unit with a lignite, which calorific value is very less, half of the coal. So we have to handle double quantity of the fuel, for which we need a huge machinery for handling the coal. And second thing is the ID fan, FD fan will be highly loaded because of the poor quality. So that's why in lignite fire plant, it is given around 10% auxiliary power consumption is allowed by the Ministry of Power, or the CE has given relaxation 10%. But normally the auxiliary power consumption will be 7 to 8%. 2% relaxation is given to NLC India Limited lignite fire boiler. If you go for the 500 megawatts and other, because they are running the steam driven boiler feed pump, their auxiliary power consumption is also very less than 5 for them, because their main drive, the boiler feed pump, is less power consumption. There is no power consumption, steam driven. So auxiliary power consumption 2 to 3%. Like this only 500 megawatt unit, not load to the 210 megawatt unit. But in 210 megawatt unit, around 7 to 8%. Lignite fire boiler 210 megawatt, it is around 10%. So auxiliary power consumption, since it is a related to the neat heat rate of the unit, heat unit of the plant. So this is also one of the factors. So if you try to reduce the auxiliary power consumption, then automatically neat heat rate also will be reduced. So normally in typical, in unit, it is 8.3% station 1. So typically 9.81% will be auxiliary power consumption in thermal power station stage 1 unit and stage 2 unit 9.2%. That 1.3% is basically coal handling systems and other, and 8% are all boiler and other auxiliaries. So these are typical things is there. Also, the auxiliary power consumption also increases with the loading of the station. It is normally found that it is what my observation, it is not brought it here. So if you maintain the unit load above 180 megawatt, then auxiliary power consumption within 8%. If it is less than that, it will be going to 9% or 8%. So auxiliary power consumption also depends on the loading of the units. How much you are. If the load is less, auxiliary power consumption will be high. So if there is a typical break-even point is NLC, it is 180 megawatt. So normally, whenever we are going, but nowadays what is going to happen, because of the technical minimum, we are maintaining the load at 140, 130 like this, 150 also. So automatically, auxiliary power consumption is also increasing. Our net heat rate also is getting increased because of this technical minimum. So this is my observations about the technical minimum. Now, I am coming to the auxiliary loads. Some few pages are there. Within 10 minutes, I'll finish it up. So you see in thermal power plant, so many pumps are available. 90% pumps will be operating. The pumps can be categorized to one is centrifugal and another positive displacement. Centrifugal, two types, radial flow, axial flow, and positive rotatory and reciprocating. Now, we have so many confusions. Sometimes people will be telling, you go for the pump in VFD. Why you are not going for VFD? It is a non-formal recommendation by the energy rate. I have argued with them. But before going to this statement, you just see. See performance of this centrifugal pump. So the this one, pump performance will decreases. This is the capacity will be decreases. This is the flow. Flow will be decreases with the reducing of the head. So if the head is reduced, automatically it depends on the flow, depends on the head. Whereas positive displacement pump, it does not depend on the head. So for constant flow pump, suppose if you want to make a constant flow pump, you have to select the positive displacement, like turbine, bearing oil supplier, pump, then seal oil supplier, because where we need the constant flow. So we have to, it not depends on the head of the tank or head of the pump. So we'll go for the positive displacement pump for the constant flow purpose. And in normal, we'll go for the centrifugal. For positive displacement pump, the efficiency is very high, all the time more or less same. But centrifugal pump, it depends on the flow. It depends on the head. So there is one maximum point is there. It is this called the best operating point. So in such case, the VFD is applicable, but not for the positive displacement. I have seen several this one energy auditing firm, they have recommended for VFD for this positive displacement. I told them for what? Because whatever the flow, whatever the thing, the head will not disturb them. Head will be remain constant. The flow will be remain. There is no need of variation of the flow. So centrifugal pump and positive displacement pump, there is a distinct difference at there. And because VFD is a very, you can say, costly matters. So don't accept such type of recommendation. You try to, or don't give such type of recommendation. Try to give the right recommendation for the pump. Now, pump efficiency, I'm not going to discuss this. It can be also possible to calculate in the local. See, the reason for the efficiency, poor efficiency of the pump, because most of the oversizing of the pump we are carrying out because of the frequency constant. Because nowadays, last 20 years, the frequency variation is not there. But previously, before this power grid taking over, the frequency variation was there. So that's why the manufacturer used to recommend a pump with because higher size pump so that the flow remain higher whenever the frequency goes down for the centrifugal pump. Then oversizing of the pump, oversizing of the so once your oversizing is there is a you can say poor efficiency will also be there. So these are all the basic reasons you have to find it out and give the right recommendations. Fan also like this, so many fans are there. It can be available in the common places. Okay, fan characteristics. See, there are three things are there. Fan is there, blower is there, compressor. If the discharge by suction is 1.1, this is called the fan. If the discharge by suction is 1.2, is called a blower. If it is more than that, it's called a compressor. They are very simplified one accommodations. So fan, blower, compressor. Compressor is the high flow, highest flow. Medium flow, low flow, fan. Okay. Now the electrical motors or 2 minutes is there. I will just went up. Okay.
Yes, sir.
Okay. So normally induction motors we are using in any thermal power plant. It goes for this one. So the efficiency 1 and efficiency 2 motors are available. Only difference is standard motor and efficiency. So if the loading level is less, the efficiency will not changes. After 50% of loading, there is a changes in the efficiency. But above 50%, there is no changes in the frequency. So EF1 and EF2, this type of motor is very effective for loading 50%. But in a standard motor, up to 75%, it remains standard. Otherwise, it will low. So 25% loading will be gaining it. So very easily, you can maintain the efficiency of the motor irrespective of the loading, lower loading, that's the energy efficient motor. Energy efficient motor are basically applicable only for motor less than 30 kilowatt. Smaller size motor have a energy efficient. Not all the motor higher size motor are highly efficient. HT motor efficiency is 95%. So there is no energy efficient motor in HT motor. The energy efficient motor is applicable only below 30 kilowatt. It is all the time we are having a confusion. People, you go for the energy efficient motor. It is not possible. Energy efficient motor for the lower size motor. It is possible to manufacture. But higher size motor, it is not possible to manufacture energy efficient. Already it is energy efficient. So that confusion you should know. Okay. So the lower size motor, how we are going to make it effectively? See, if the loading level is greater than 75% of the motor, no need of changing the motor. Because the energy efficient motor, efficiency of the energy efficiency motor up to 50%. So if the motor loading is 75 to 50%, energy efficient motor. Motor level is less than, you change the motor capacity to lowest. And motor loading is less than 40%, you can change the delta motor to the star motor. So this is the recommendations I had implemented in my plan and run it successfully so that it was used very properly without any less investment. So because investment also is a very, very important factor. Now stray losses. Basically, compressor. The efficiency of the compressor is very less. So compressor, the loading, you can say this one leak, compressor leak can be calculated, very easy formula. Loading time and you have to start the compressor and see how much loading time it takes. You can see the current and you can and a stopwatch. So loading time you will get it. And this loading, unloading time also measured. So loading time divided by total time is called the leakage into percent of capacity. So it was the leakage. So that much. If the leakage is more, you give the recommendation accordingly. That is called the leak test. So compressor system, very easily you can find it out. Then the steam losses or other steam leaks are there. So you can also have a calculations accordingly. If you have this one, automatically you can able to control. Then the insulation losses. So nowadays the thermal imaging camera is available. You take the photograph where there is a peeling off of insulation is there, and you give the calculation accordingly, and it will take this much of energy loss will be there, or the fuel loss will be there due to dispatching. Okay. Now the final report. This final report format is very, very important. These are the points to be mentioned. Acknowledgement. In the acknowledgement itself, the name of the unit head, energy auditing team, including the energy manager team should be recommended. Then brief profile of the energy auditing firm. The energy auditing firm, what you are engaging, their brief profile has to be given. How many accredited energy auditors are there? How many energy audit work out there? Their name and profile should be there. Then brief description of the plant, because the plant locations is very important. So all the brief data, so like name of the plant, address of the plant, climatic conditions, atmospheric average ambient temperature, then government or private, how it is location is, all the decisions, when it was commissioned, what are the present status, like that they have to mention everything, brief description. Then people can able to understand. It was not there previously. I maintain all these things in my latest energy audit report in NLC. Then executive summary of the audit report, because this report goes to the top management. So executive should understand by reading 2 pages what is the condition. So it should be graphically, and all the key reports should be mentioned there. Then the details report should be formatted, should be calculated and given. And finally, the calibration certificate of the hand equipment should be mentioned in that. So this is the final report format. Otherwise, the people will not be able to understand what the energy auditor is. Okay, that's it. Thank you. Any question is there? If you have any technical assistance regarding the energy management or electrical things, you can contact me. My WhatsApp number is there. My email ID is there. And second thing, I have published one book. It is available in the Amazon. It's cost about 147 rupees, or in Kindle it will be free. Where all the calculations and formula I have mentioned. You can take this book as a reference. I hope this is a presentation for this day. I do not know what is the feedback. If you have a time, the participants, you can give a feedback to me, so that next time I can prepare in better way. How much it has gone to you, I do not know. But if you kindly give a feedback to me in my WhatsApp number, I'll be very happy. And if you, at the same time, if you have any doubt, you can ask me. In my free time, I will try to respond. Any energy consultancy, you can give a question to me, I can help you. So that is the end of my session. I think I have concluded in the right time. Is it, Sam?
Yes, sir.
Okay.
Sure, sir.
Okay.
Wonderful presentation, sir.
Okay, very good. So it has gone to the people. It has reached properly.
Yes, sir.
I do not.
Someone is unmuting. They are trying to
Okay.
ask some questions. I think
Okay,
so.
okay. Any question?
Yes, participants.
Sir, good evening, sir.
Yes.
Yes, sir. Thanks for a wonderful presentation, sir.
Okay. I have reached it properly or not?
Yes, sir.
Okay,
Because I was trained at NPTI, National Power Training Institute, 2008, sir. But I was there, luckily, TPS 1. But I'm very happy to see your presentation for TPS 2 on the energy auditing reports, and it was wonderful,
Okay,
sir.
okay.
It was wonderful because we got a good insight on the steps how to do an energy audit.
Yes, yes,
It
yes,
just
yes.
enlightened us.
Yes.
Sir, my queries are just one thing that for a condenser pressure, if I wanted to, it is going lesser. What's the main reason it will go, sir?
Condenser pressure.
Yes,
That means
yes.
your vacuum is less. That's why condenser pressure is losing. There is a leak maybe there in condenser. Vacuum is going. You are losing the vacuum.
Okay, sir. Okay.
So that I have given one chart is there. I have given one chart. You take the data and put in the chart, and you can able to identify yourself.
Okay,
what is
sir.
the reason behind
Thank you, sir. Okay.
Okay.
Sir.
And
Okay,
I tell you, you can refer my book also, or you can personally give me data. I can calculate. Your name, please. Your name.
Sir, my name is Jiva, sir. Jiva. Yes.
Jiva. Okay.
Yes, sir.
Jiva.
B.
Jiva. Where you are working now?
Sir, now I'm in teaching, sir. I'm working as assistant professor in Kumaraguru College of Technology, sir.
Okay, good. Very nice, very nice, very nice. Okay, thank you. Very nice. You can go ahead. Okay. Any other questions?
Participants, any other questions? Sir, we are not getting
properly.
you, sir. No, I think.
If it is not, they can WhatsApp me in my number.
Yeah, sure, sir.
I can give it.
Thank you very much. Yes, sir. Thank you very much for spending your valuable time with us, sir.
Okay, good, very
And
nice.
the session
I am
also
ready to
very
serve.
informative.
I am here to serve, no problem. You can contact me anytime. I can carry it out. But only difficulties in the online, I cannot see the reactions of the participants. That is
Yeah, sure.
That's the thing. Okay, anyway, the things we have to do. So any queries, anything from your side, from your organizer?
No, sir.
Okay, thank you. So that's the end of this. Thank you very much for giving my opportunity to express my ideas and educated the younger generation. Okay, thank you.
Thank you, sir.
Thank you, sir. Good.
Thank you. Thank you.
Thank you, sir.
Good. Okay.
Participants, please submit your feedback on attendance form, which is shared through WhatsApp as well as through registered email. We'll see you tomorrow. Thank you.